Today, we're tackling a massive question in cancer research, something I like to call the immunotherapy puzzle. Why is it that these incredible game-changing treatments can work miracles for some people, but for others, they don't? Let's get right into it. This is the core mystery that doctors and scientists are grappling with every single day. You have a revolutionary drug that completely saves one patient's life, but then it does almost nothing for another patient who has the exact same type of cancer. This isn't just some academic puzzle, we're talking about real life or death outcomes here. Just look at this scenario. It's pretty stark. You've got patient A and patient B. Both have colorectal cancer. Both get the exact same immunotherapy treatment. But look at the results. Patient A has a complete response. The cancer is gone. But for patient B, the disease just keeps progressing. So what on earth is the difference? What is that one crucial thing that leads to such totally different endings? For the longest time, the best guess that scientists had was pretty straightforward. It was all about counting, specifically counting the number of mutations a tumor had. The thinking was, the more mutations, the more foreign it looks to your immune system, and the easier it should be to attack. So this idea got a name, tumor mutational burden, or TMB for short. It's really just a simple measurement. You count up all the mutations in the cancer cell's DNA. And the theory was simple too. More mutations equals more targets for the immune system to lock onto. But, and this is a big but, as we saw with patients like patient B, just counting things up clearly isn't the whole story. It's just a piece of the puzzle. Right. So that got researchers thinking, what if we're looking at this all wrong? What if it's not about just counting targets? What if we need to get smarter and actually assess the enemy? Okay, to really wrap our heads around this new way of thinking, let's use a metaphor. It's simple, but it's really powerful. I want you to think of a tumor as an enemy army. It's growing, it's adapting, and it's trying its best to avoid being defeated. Okay, so those mutations we were talking about, they create something called neoantigens. Now, in our army metaphor, these neoantigens are basically the enemy's uniform. They're these unique flags on the surface of every cancer cell that scream, hey, I'm an invader. And that's the key. It's these uniforms, these neoantigens, that allow our immune system, which is our body's own personal army, to spot the cancer cells and launch an attack. Our immune system is trained to recognize anything that isn't supposed to be there, and these uniforms are a dead giveaway. So, if we're really going to understand this battlefield, we can't just stand on the sidelines and count uniforms, right? We need a better strategy. And that's exactly what a new study did. They built a super sophisticated computer model to simulate the entire war, moving way beyond simple counts to a full dynamic simulation. And the model basically works with a two-part punch. First, it simulates the tumor's evolution, how that enemy army grows and changes its tactics over time. Then, step 2, it simulates our immune system's attack when we add immunotherapy, basically how our army fights back when we send in reinforcements. And after running tons of these simulations, all based on data from real clinical trials, they had a major breakthrough. This is the aha moment. It's the structure of the neoantigens, not just their number, that really determines whether immunotherapy works or not. In other words, it's not just about how many enemy soldiers there are. It's about what their uniforms actually look like. Let's break that down. Think of an easy target. This is an army with strong clonal neoantigens. The whole army is wearing the same bright, obvious neon pink uniform. Super easy for our immune system to spot, right? But then you've got a hard target. This army has weak, heterogeneous neoantigens. It's like a chaotic mess of soldiers all wearing different muted camouflage. It makes it incredibly difficult for our immune army to mount a coordinated attack. But here's where it gets even more fascinating. And frankly, a little counterintuitive. This deeper understanding led them to something they call the weakest link theory. And it's a totally new way to predict if a treatment will work. So, get this. The crucial point of this theory is that the whole battle isn't decided by the enemy soldier you can see the easiest. Nope. It's all about the one you can barely see. That one soldier with the best camouflage, that's your weakest link. He's the one most likely to survive the first wave of attack. And that one survivor can then go on to build a whole new army that's resistant to the therapy. The weakest link can literally decide the outcome of the war. Okay, so a computer model is cool and all, but does it actually hold up? Does it match what really happens with actual patients in the clinic? How well does this code stack up against clinical reality? Well, the results were pretty amazing. They tested the model against data from a huge clinical trial called Keynote 177. And it wasn't just that it got the basics right. It successfully reproduced real-world patient response rates, their survival curves, and it even captured some of the really weird, complex things that doctors see but have struggled to explain, like pseudoprogression, where a tumor actually looks like it's getting bigger before it shrinks, and even the delayed resistance that pops up months down the line. Now, we gotta be real here. No model is perfect. On the plus side, its biggest strength is that it gives us causal insight. It helps us understand the why behind success or failure. It's built on real clinical data, and it points to totally new predictors. But on the flip side, it's still a simulation. It has to simplify some of the incredibly complex immune system dynamics. And, this is a big one, it hasn't been tested yet on a new group of patients to prove its predictive power going forward. So what does this all mean? Where does this leave us? Well, this whole new way of thinking is really opening up an entirely new frontier for creating the next generation of biomarkers. The possibilities here are genuinely exciting. We're talking about new biomarkers that go way beyond just counting mutations. We could start combining imaging data with this kind of neoantigen analysis for a much richer picture. We could use these models to design smarter combination therapies from the get-go. And the ultimate goal, the big dream, it's the idea of personalized digital twins, a perfect simulation of a patient's own cancer, where doctors could test out different treatments virtually to find the absolute best one for you before you even take a single pill. And that brings us back to the final, really provocative question. Could we one day actually predict how you're going to respond to a drug before you ever take it? What's so amazing is that this research suggests we're getting closer than ever to making that science fiction a clinical reality.